So the question here is, how do I come up with a parameterization for a surface, particularly when that surface is being understood as the graph of a function of two variables? So the moral, remember, of parameterizing a surface is we have to figure out how to distinguish all the different points on that surface by a choice of two parameters. So what two quantities could you tell me, and could I then use to produce a point on this surface? Starting with a surface which is the graph of a function. So here we have z equals x squared minus y squared. So this is a graph of the function f of x and y equals x squared minus y squared. So just to sort of set our terminology here, when I say graph of a function, that is what I mean. So this is a graph of the function f of xy equals x squared minus y squared. And so the secret, not really a secret because I'm about to give it away, right? The secret of when we graph an equation like this one using a technological tool like GeoGebra, I'm going to write in f of xy equals x squared minus y squared. Oops, I got to get into our 3D mode. Otherwise, it's not going to make any sense. F of x and y equals x squared minus y squared. So here is the picture that GeoGebra comes up with for the graph of this surface. So this is called a saddle, maybe for some obvious reasons, like the saddle on a horse. It sort of goes down in one direction and it goes up in the other direction. So the x-axis direction, if I flip us into our usual orientation here, in the x direction, it looks like that's the direction that my saddle is curving upward, so that would follow sort of the contour of the back of the horse. And then the y direction, it's sort of going downward, and so that would follow the direction that I would put my legs down, sort of down the sides of the horse. So that's why they call this a saddle surface. And so our job is supposed to be to find a parameterization for this surface. And here's the secret that that I'm going to kind of give away a little bit here. The secret is that how most graphing utilities how most graphing utilities graph a surface is by parameterizing it. And you can see the telltale signs of that parameterization. Let me hide this plane here for a minute. You can see that there's a sort of a cross-hatched grid that's laying down on top of this surface. Those grid lines are exactly those sort of trace lines that we had on the surface over here before, because those lines are actually just the vertical traces of this surface through vertical planes in 3 space. And if you don't believe me, let's just try. Let's just take k, set it equal to some constant, and then look at the vertical plane. Let's say y equals k. Right. So this vertical plane, y equals k, when it slices through this surface, is giving me, it's matching up with all of those lines that are going in the sort of x-axis direction. Right? And all those traces end up being parameterized curves, and those parameterized curves in this example end up being just these parabolas. Right? If I set y equal to a constant, my traces are going to look like z equals x squared minus a constant, which is something that in the xz direction looks just like a parabola. So if I look in the xz plane here, so face down the y-axis, all of these intersections, you can kind of see the shadow of them there. Those intersections are all just parabolas pointing upwards. And the same thing with the x equals k traces. That the x equals k traces are also parabolas. They just happen to be parabolas pointing downward. Because if I set x equal to a constant, I'm going to get something like z equals a constant minus y squared. And in the xz planes, in the yz plane, those are all going to be parabolas that are pointing downward. So in what sense is this a parameterization of the surface? Well, it's a parameterization in the sense that the graph of any function passes the vertical line test, right? Because that's what functions do. If you give a function a value of x and a value of y, it's going to produce for you a unique value of f of x and y. And that value of f of x and y is otherwise known as the z-coordinate of the corresponding point on this graph. That's what it means to be a graph. And so any graph of a function can be parameterized just by taking my parameters to be the independent variables to my function. In other words, my function takes two variables x and y, and those two variables then parameterize. They can parameterize the surface that is the graph of the function. So just to sort of underline what I mean here, when I parameterize the graph of a function, I'm trying to find ways of describing the coordinates of all the points, x, y, and z, on my surface using only two parameters. So sometimes I think of parameterization as a process of starting with x, y, and z just equaling themselves, and then trying to reduce the number of variables on the right-hand sides of those equations down to 2 instead of 3, by finding a relationship among x, y, and z. And the relationship that exists among x, y, and z for the graph of a function is that the z value is equal to f of the x and y values. And so that means that I can get the z out of the right-hand sides of my equation here just by replacing it by f of x and y. And once I've done that, I now have the whole right-hand sides of this parameterization expressed in terms of two quantities, x and y. And so I will just make x and y my parameters, s and t. So if I want to parameterize this saddle surface, so coming back to the homework problem, the way that I would do it is, again, just sort of starting by writing out x equals, y equals, z equals, and then just making them themselves on that right-hand side. I'll just ask, well, what relationship can I find among the variables x, y, and z that can eliminate one of those variables from this description? And the relationship is exactly this one, right? The relationship which is defined by the equation of this surface. So if I replace z by x squared minus y squared, then what I have is already a parameterization of this surface. It's just that the parameters, x and y, look like sort of meaningful variables in the rectangular coordinate system, and generally in a parameterization we'll replace them with meaningless parameter names. So let's replace x by a parameter called s, let's replace y by a parameter called t, and then we'll sort of forget that those were there. And if I do that, then I would replace the x and the y in this equation down here also with s and t, respectively. And so at the end of this process, what we have is coordinate equations. I can determine the x-coordinate and the y-coordinate and the z-coordinate of any point on this surface using these functions of s and t. Right? You give me an s and a t, I'm going to make the s the x-coordinate, I'm going to make the t the y-coordinate, and then I'm going to figure out the z-coordinate by taking s squared minus t squared. So I can write these as three separate coordinate equations, or I can package them into a vector-valued function, the way that we did with parameterized curves. U of s and t is s comma t comma s squared minus t squared. So this is more or less a recipe for any time we are trying to parameterize a surface where we're understanding that surface as the graph of a function. We can just take the independent variables in my function to be the parameters, be the two parameters for my surface. And then the third one is just determined by the function applied to the other two.